when I calculate derivative, I have I omega, then I have capital Y E I omega t, yes? And then capital Y E I omega t is small y. I'm just use the first equation every time. I'm differentiating and then I'm using the first equation. So I'm having like this. M y double dot plus c y dot plus k y equals this. So look what I get. We have k times y, so it's the same. Now I have minus m. Second derivative gives me omega square, but then it is y. Then cy dot gives me ic omega, and then first derivative is ic omega, and then y equals p0 ei omega t. So this is particular solution. Are you with me? If you are gone somewhere else, then tell me. I'll catch you there and bring you back. So I get y of t. Y of t equals on the right-hand side divided by the left-hand side. P sub 0 ei omega t divided by k minus m omega square plus ic omega. Now I have this blue expression. This blue expression is complex. In denominator is complex, I omega. I don't like complexities in denominators. I don't like complexities in denominators. Therefore, I will multiply complex conjugate of denominator, k minus m omega square minus ic omega. But I cannot just multiply by this. I will multiply also numerator by this. So this is 1. I will multiply, I will take the plus and minus. And the same here. Now, what denominator is very easy to deal with. Now, then it is, look please, that is complex conjugates multiply. So therefore, it's this real part, k minus m omega squared plus this guy squared, cm squared. Because that is like a plus b times a minus b. That equals a squared minus b squared. So this squared minus this guy squared. But I squared is minus 1. So I said minus, so I will get plus c squared omega squared. So in the denominator, I don't have any complexities. In the numerator, I do have. And that is, look, this time, this P0 times this, times e in power omega t. Now this e I omega t is cosine omega t plus I sine omega t. So now I will find immediately x of t. X of t, I said, is real part of y of t. So therefore, I don't need to write everything there. P0, this times real part, cosine omega t. Then this times imaginary part. So minus I with plus I will give me plus c omega sine omega t. You see, I got so cheaply a particular solution in few steps just. Particular solution does not depend upon There is no complexities there. Everything is real. That is how it should be. You agree with this? I think it was neat. Neat way to get a particular solution. Now let us just, if you wrote this, did you write this? If you write this, it is interesting what happens at the resonance. At the resonance, this omega square, k minus m omega square is 0. But denominator is not 0. So therefore, this x of t does not go to infinity. It goes to a big number, but it does not go to infinity. So you may want to write, at resonance, k minus m omega square goes to 0, but x of t does not go to infinity. It is bigger because, look please, this is positive and this is positive. So there are two positive quantities here. But one of the positive quantities is 0, so therefore this is bigger than otherwise. This expression at resonance is bigger than if there is no resonance, because when there is no resonance, this is present here. So we are adding something to this. But maximum anyways does not occur at 1, at omega equals omega, somewhere else. So this can be written like this. Now pay attention. Please, but first you listen to me, then you write. Over there is cosine omega t and sine omega t. I don't want to have them both. I would like to have phase shift. So therefore, I should multiply and divide by this square plus this square and square root from there. Then when I divide by that, this divided by that square root will be cosine phi. And this will be sine phi. So therefore, what I did is as follows. Look, please. This equals P0. Now I take this square root of this square plus this square. And I have in the denominator. Square root. Actually, I did not need this. I did not need. Here it's sum of the squares. I can represent it as square root of it times square root of it. Okay, look. Here is this expression. So I can take square root of it and then square root of it. Then I will say this divided by this plus squared plus this squared is 1. Because look, it so happens k minus m omega squared c omega. So therefore, this is cosine alpha, this is sine alpha, or if you want, phi. We are just trying to write it short, short notation, if it is possible. So x of t then is very nice. P sub 0 square root k minus m omega square squared plus c square omega square times cosine omega t minus alpha, or phi if you want. Tangents alpha equals c omega k minus m omega squared. So it's a bit algebra, but it's a very simple algebra. Okay, here, m omega squared. Any questions up to now? That is all particular solution. Still, it is not a general solution, just a particular solution. But particular solution shows that complex numbers are super useful. because by them we got very, very easily the solution. Now, complete solution is a sum of complementary solution and particular solution. So consider underdamped case. In underdamped, do you remember this solution we had today I started? C1 cosine omega dt plus C2 sine omega dt in power minus z omega 0 t. Then plus this particular solution. Because forced vibration, it is actually a summation of free vibrations plus one particular solution. Because what is a complementary solution? Complementary solution is solution when right-hand side is 0. So that is actually free vibration. So forced vibration is free vibration plus one particular solution, just any. Or, this can be written as we wrote before, A cosine omega dt minus phi in power minus z omega 0 t, and here is alpha. There is t, there is phi there, and alpha here. C1 and C2, or A and phi from initial conditions. Now we got an unbelievably interesting result. You know, we can say life is beautiful because result is unbelievably magnificent. What we got is as follows. Look, please, with forced vibration, this guy, that is a complementary solution. It depends upon initial conditions. When time goes on, this diminishes. But this stays. So that means that physically complete solution is a sum of something that goes away transient. It's a transient solution, which is a complementary solution, which decreases exponentially with time. So there is something transient, and then something that stays forever. And this is particular solution. And look, when t goes to infinity, this stays. So this is called steady state vibration. Steady state. Transient, steady state. We call it transient because there is e in power minus something t. Because it disappears at t is big. It's gone. Very often, if zeta is a bit sizable, then it goes very, very fast. It's gone. So there is some initial effect, and then there is something that stays forever. At least in this differential equation. We have a linear differential equation, and that is what happens in a linear differential equation. So, and that is called steady state vibration. So, therefore, it makes sense to concentrate on this. Let us concentrate on steady state vibration. Steady state vibration is something we get when time goes on. So, x of t equals p0, k minus omega squared squared plus c squared omega squared square root, cosine omega t minus alpha. Or it is capital X times cosine omega t minus alpha. This capital X is called amplitude of steady forced vibration. Amplitude. And this X equals this expression. So now I can also put it like this. I can calculate static displacement. If this load, my load is P sub 0 cosine omega t. But if the amplitude of the load were applied statically, if the amplitude of the load were to be applied statically, then displacement would be x static equals P over K. If, so you should write, or were amplitude of the loading applied statically, then that would result in static displacement, which is P0 over K. So then we can calculate x over x static. X over f static is P0 divided by the square root, and then divided by x static, or multiplied by the opposite, K over P sub 0. So then P sub 0 is gone. We don't want this P sub 0. Then there is a 1. Now there is, so this guy is divided by K. So K comes here, so this K is, instead of K, I get 1. Minus M over K. This is omega sub 0 squared. 1 over omega sub 0 squared. Omega squared. Plus C omega K squared. What I would like to find, actually, what I'm after. I'm after some non-dimensional figure. I want to find non-dimensional representation. So therefore, I decided to divide x by x static. Because x divided by x static, I mean, they have the same dimensions. Because they have the same dimensions, that's this non-dimensional quantity. So I get a very nice thing. 1 minus m squared, omega squared divided by omega 0 squared. Plus, and there is C omega over K. Now you probably guess that we will bring this zeta also into play. Okay, resonance naturally is omega equals omega sub 0. So when there is a resonance, this first term disappears. But x, or this ratio, x over x static, does not go to infinity. It will go to some big value. Depends on zeta. Depends on the damping. And we will get it. Now, zeta equals C over 2m omega sub 0, or C over C critical. So C critical we already calculated, 2 square root of Km. So therefore, we can write down that C equals C critical times zeta. Now we have there C omega, 2m omega sub 0 zeta, that is C. 2m omega sub 0 zeta times omega divided by k. This equals 2m omega sub 0 zeta omega 0. I multiply and divide. Omega over omega 0 k. So I now want to have this omega over omega sub 0 also here. So then we have this equals, okay, 2m omega 0 squared. Omega 0 squared is k over m. Zeta over k, omega over omega 0. So then this will be, yeah, k and k are gone, m and m are gone. 2 zeta omega 0, omega over omega 0. We get a very beautiful expression. There is no m and k and c. We have 2 zeta times omega over omega 0. We get a very, 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 very beautiful expression. I said 6 times, so I could have said 7 times. Now what I have to do is to plug this back. So instead of there, I should write this squared. X over x static equals, look please, 1 divided by square root 1 minus m omega over omega sub 0 squared plus 2 zeta omega over omega sub 0 squared. I think it's very nice and very simple expression. You too in your work try always to introduce some non-dimensional quantities. Whether you are in mechanical engineering or business administration, anywhere. Some people are doing degrees also jointly with business administration. It's always good to have non-dimensional quantity because we see effects directly. Now I can introduce small r, which is omega over omega sub 0, ratio of the frequency of applied force to the natural frequency. That is this ratio. So we get like this, x over x static equals 1 over square root 1 minus r squared plus 2 zeta r squared. This is called dynamic magnification factor, or gain. Why it's called magnification factor? Because it is this many times response is bigger than static. This many times. Now, phenomenon of resonance is that when the frequency of the applied force equals to the natural frequency, the amplitude of forced vibration is large for practical values of damping. If zeta is natural, look, if zeta was small, or 0, then this goes to infinity. But zeta, if it is not 0, then it is something, but therefore it does not go to infinity. Look. If this zeta is 0, then when this is 1, when r is 1, then naturally this goes to infinity. But now, when r equals 1, this does not go to infinity, depends on the damping. Depends on, because this is 1, yes? So it depends on 2 zeta. I'll show you the picture. This is a picture. So this is zeta equals 0, then zeta equals 0.1, zeta equals 0.2, zeta equals 0.5, etc. Smaller the zeta, bigger the maximum. Paying attention that maximum is not at 1. It is a bit shifted. As you see, this maximum is not at 1, but at some other value. Because there is, we have 1 minus r squared plus something. Because there is something that we have to calculate. I'll show you next time where this maximum is. But now, if there is a damping, then solution does not go to infinity, but still it could be very large. So therefore, resonance is not just artifact of idealization, means I just did not take into account damping. It is actually physical phenomenon. But without damping, solution goes to infinity. With damping, it does not go to infinity, it goes to large value. So it is, look here, 5. So in this case, maximum equals 5, then 6, or something more. Yes, abscissa is r, small r, omega over omega sub 0. So response to forced vibration, variation of dynamic magnification factor versus frequency ratio for values of damping factor, zeta. Yes, similarity is that it goes like that graph, but then it does not go to infinity, it just bends and has a maximum. So that curve is good in the beginning. Later it becomes not very good. But that is what theory is. I mean, depends on the theory, what kind of theory we are using. Any questions? Okay, if we have no questions, we will finish today 1 minute and 10 seconds earlier, because I would like to ask you where are you studying and which department and what is your major, etc.